Hello everyone, welcome to the week 6 of problem solving session for the Theory of Computation course. So last time we saw a brief discussion about the non-deterministic and deterministic PDAs. Okay, and now we'll look at the third model of this course, which is called Turing machines. Okay, so how do we define this? This is a 7 tuple which consists of q sigma gamma delta, the start state, the accept state, and the reject state. So I won't write the usual ones. This is the set of states. This is the alphabet of the input. This is the tape alphabet. Okay, so yeah. Okay, so this is the head position, which tells you at any point of time uh, what is that cell at which you are looking at. So there is some content written on this, maybe A, B, B, C, something like this. Okay, and then there are some blank symbols. Okay, so initially your input that's given to you should belong to every letter should belong to the alphabet sigma, whereas when you write over it you can change the alphabet, so you can work with a larger alphabet when you are rewriting, similar to PDAs where you were allowed to have a stack alphabet, which is different. So this is your sorry this is your tape alphabet. Okay, and this is the start state. This is the accept state, and this is the reject state. Okay, so unlike the definitions that you have seen so far, so far what you have seen is if you reach an accept state at the end of the input, then you should accept. Whereas one difference that Turing machine models have is that they can keep moving left or right to back and forth. So the way we define this transition function delta is that you yeah is that you look at the tape alphabet, you look at the current state that you are in, you decide which state to go to, which what alphabet to write, and you can go to the left, you can go to the right, or you can go to the or you can stay at the same cell. These are the three things you can do, and therefore at any point of time you are here, you read this, you decide whether to change the contents of it, and then you can go here or stay wherever you are, and you keep on doing this. So given this transition function, you would have changed the input over and over again. So there is no such thing as once you end up in an at the end of input, if you reach into an accept state, then you accept it and so on. That doesn't make sense because you could keep moving. Therefore you need a different notion here, which is different from what you had earlier. So you say that this QA and QR, these are two special states of the machine. If you ever end up in this state, then you should just accept and halt the computation. And if you ever reach the reject state, then you're always going, like if you reach that state, then you are done, then you are going to reject the string. Okay, and yeah, so is the model clear?
So can there be multiple accepting states and multiple states for rejection?
Yeah, you can do that, but eventually you can, I mean, it will be equivalent. You can say that you can come up with an equivalent Turing machine where there is only one accept state.
How?
So let's say that M1 is your machine where QA1 and QA2, these are the final states, and I'm not writing the rest of the things. So that means if you ever reach QA1 or you ever reach QA2, you are always going to stay there, and end up accepting. Now what you could do is uh, yeah, you come up with an M prime where QA1, whenever you reach it, you're always going to um, move to this new state queue. Okay, if you ever reach this, all you are going to do is just go to queue. And similarly, if you are at QA2, you immediately go to queue. Okay, so then now this queue acts like a new final state, and no matter what you see from this point, you are always going to accept.
Oh, and what would be the level of transition? I mean, what will I read from the tape while making a move
No
from
matter
Q?
what you read, yeah. So so what you will do is delta of QA1 on, so this should be every tape alphabet. For every tape symbol, you will write QA. Um, yeah, I mean, it doesn't really matter what you write at this point, and yeah, whether you go to the left or right, but maybe let's go to the.
And how do we represent the states for rejection? I mean, like a double circle represents the accepting state, and then for the rejection state.
Mm, it's just a matter of convention. I'm not sure if it's standard to do it this way, but yeah.
So I mean, apart from the accepting states and the rejection states, can there be other states as well?
Yeah, other states will be in queue. Yeah, but these are the special states that we have.
So then how to represent the rejecting states then?
Well, I mean, you have already. I mean, in the beginning itself, in the description, you have told that is going to be your accept state and QR is going to be your reject state. So technically, you don't even need to draw these double circles, right? Because if you just see a QA here, you know that it's an accept state.
Okay. So again, there is a slight notational difference, and I'm afraid that that may lead to the change in the design of the Turing machine as well, because in some books they used to describe the seven tuple as they define the final states QA, and then blank is the seventh element. That blank, which is not the part of the sigma, is the seventh element. And however, they do not explicitly define the rejecting states. So my viewpoint is that all those states which are not accepting states are the states of rejection.
Hmm.
Like their seven
Okay,
tuple
that
is
is.
Q, sigma, delta, Q naught, F. Till here the things are same as
Yeah.
Fahrenheit.
So that is not necessarily true because see, if let's say all the states are either accepting or rejecting, okay. I mean that's what that definition essentially means, no?
Yes.
Yeah. Then what will happen is on every input, the Turing machine is either going to accept or it's going to reject. That means it's decidable.
So in that case, what happens that the Turing machine may enter into a loop as well. That
Hmm.
is possible because of the left and the right movement.
No, but by definition, what we said is if you ever reach a QA and accept state, then you are going to. I mean, it's basically if you touch that state, then you have to accept, and if you touch a QR state, then you have to reject.
Oh, I see. So their definition in that case could be that if we are able to reach to the final state, the string is accepted, and the in the second scenario may arise wherein the string may be rejected or may enter into a loop. Loop in the sense that if I keep on, I mean, oscillating in
Right,
between
right, right.
states, like left because of the left and the right movement. So I mean, and this definition is also being widely used. So I mean, in this definition, what is possible? QA plus QR plus something is equal to Q. Is
Hmm,
this
hmm,
or
hmm. Yeah, yeah.
okay?
Um, okay. I mean, technically, what we're saying is Q is the set of other states, and out of which. I mean,
Some
it shouldn't matter. I mean, it shouldn't matter, right? Because I could make Q have these states into it, in which case Q contains all the other states, all the three states. Otherwise, it's not a valid description. Or I could say that, okay, these are three different states outside Q. It shouldn't matter.
okay, okay, all right, fine. Thanks.
Okay, yeah, any other questions? Okay, good. So, okay, let's do this question.
Which statement best describes a decider? A Turing machine that holds on all accepting strings but may loop on others. A Turing machine that holds on every input string, evaluating, eventually either accepting or rejecting. A Turing machine that has only one tape. The machine that uses non-determinism to find a solution. So answer is two. That I mean gives the answer of yes and no both.
Correct, yeah. So, yeah, this is the correct answer. So, when we say, so let's say L is a language, so L is a subset of sigma star, and we say that L is recursively enumerable if and only if there is a Turing machine M such that uh, M accepts X whenever X is in L, and we say that L is uh, decidable or recursive. Both are widely used notions and both mean the same essentially. If there is a Turing machine M such that uh, M accepts X if and only if X is in the language L. That means if a string is in the language, then the Turing machine M must accept it. If X is not in the language, then the Turing machine M must reject it. If that happens, then we say that the language is decidable. Otherwise, this is also called semi decidable. Okay, so here what we are saying is that the machine must accept whenever X is in the language. If X is not in the language, then the machine may accept, may reject, or may uh, keep looping. Okay, so there is no guarantee that it's going to halt in the first place. It may just keep on running forever. Okay, so uh, by definition, what we know is that this is the set of all semi-decidable languages. Then the set of decidable languages must be inside it, because any language that's decidable is also semi-decidable.
Yes.
Okay, and
So
yeah,
in this definition, something else needs to be written like M rejects X if X is not the
which one?
part of.
This one or this one?
Oh, in the second. Oh, you use if and
If
only
and
if
only
kind.
if, yeah.
All right. Yeah, fine.
Okay.
So any specific reason for calling them as recursive or
Yeah,
enumerable? Enumerable makes sense that probably we would be able to enumerate the things somehow. But what
yeah,
this recursive here means?
yeah. So this enumerable does come from the fact that there is an equivalent model called enumerator, and yeah, and therefore this term, but I don't know why exactly. This has nothing to do with that kind of recursion, as in, the sub problem kind of recursion. I don't know where this term came from. Yeah.
Okay. All right. Yeah.
Ma'am, give an example, say tuning machine that has only one step.
Okay, so by definition, you make the machine have, at least like this okay, not three but at least two, right? You need an accept state, you need a reject state. They may not be reachable, but you can
Okay.
but you can come up with two state machine. Let's say QA itself is your start state and also your accept state, and QR is this. And here, no matter what happens, you are always going to stay on this state. Like read something, write the same thing. Whatever you read on the tape, you stay in the same state, write the same thing, and let's say keep moving to the right or keep moving to the left, anything. But then what will happen is it will accept all the languages because you started at QA, right? So then there is no way that you can get out of it.
What about the cleaning closure of sigma? How to design the Turing machine for that?
Yeah, so this machine will accept sigma star, right? um, yeah, no matter what input is written on the tape, it will end up accepting that input.
What is the level of the self loop here in this Turing machine? Do you think?
Level of self loop as in?
Level, I mean, for which input symbol are we making a transition?
So the transitions are as follows. Yes. So you are at QA, then let's say B is for all B in sigma. Okay, not really sigma, but the tape alphabet. What you will do is you stay at QA, you write the same thing, and let's say you, it doesn't really matter whether you go to the left or right or stay, but yeah, this is the transition that you will make.
So in the case of the Turing machine, it is not necessary to scan the entire string,
Hmm.
and whenever I reach to the accepting state, I will. Okay. So the easiest way to convert a finite automata to the Turing machine would be that I keep on moving towards right.
Exactly, yeah.
Oh, I see. So in this case, then I can write say delta QA comma B is equal to QA comma B comma R, and I keep on moving towards R,
Hmm.
and then I can write what this B as an element of sigma as well, and I keep on moving towards R.
Hmm. Yeah, in fact, you are whatever you are going to read here, you'll always write the same thing if you follow the DFA construction, because DFA is not allowed to change the input.
So I mean I am unable to think of an example of a Turing machine wherein accepting state and final state both are being used. And
Accepting state and
apart from the accepting and the final accepting and the rejection state, there are other states as well.
hmm.
So I mean, if you
Okay.
can show me any Turing machine.
Okay, so you have seen this example probably, right? A to the n, B to the n, C to the n, n greater than equal to 0. Um, so, how will you do this with a Turing machine? What's the, like, let's just first see what is the high level description. And also, I'm assuming that the tape is infinite in towards the right. So, let's say this is the left hand marker, okay, and after this there is going to be input, and then there are infinitely many cells to the right. There is an equivalent model where the tape is infinite in both the directions. Okay, so the other this is a single tape model, and not really single tape but one way infinite. The other one would be that you have infinite cells on both the sides, here and here, and your content is, let's say, start somewhere here. Okay, so both of these are equivalent. I guess you can already see why.
Okay, so next question: design a tuning machine that convert a binary string into its equivalent unary string.
Yeah, we are not done with this, no? Uh, let's see this first.
Okay, okay, continue.
So yeah, two-way is equivalent to one way. In fact, whatever modification we make, I mean, is going to be same as the standard Turing machine only, capability wise.
Sorry, can you repeat? Mm.
Yeah. So I mean, if I extend the design of a Turing machine by including the multiple number of the heads or the multiple number of the tapes, computationally that is equivalent to the standard Turing machine only, having a single tape and then that stuff. So
Yeah, so, yeah, that I agree. But this question is somewhat different. We are saying both of these are single tapes only, right? This is a single tape where here you have like this left end is bounded. It is infinite towards the right, whereas this model is you have infinite number of space to the left and infinite amount of space to the right. Both are single tapes, but one is finite towards the right, the other is finite in both directions. So why are these two models equivalent?
so there is a proof for it, and that would be that I can use some, because this this two-way infinite can be viewed as a single one-way infinite having two tracks. I guess no.
Yeah, so this is similar to the proof of why the total number of natural numbers is equicardinal to the number of even natural numbers. Basically, what you do is, let's say these are the cell numbers, then um, yeah, let's say this is where I decide to keep a marker, and everything, there is infinite number of things to the left, infinite number of things to the right. Then what you do is, for every content, let me just color this. These are blue and these are red. Okay, so what you do is, think that think of it this way. Let's say these are color coded with blue and the things to the right are color coded with red. What you do is, take the first content from here and put it here, take the second content of here and put it on the odd numbered cells in this tape alternately. So this will go here, this will go here, this will go here, and so on. Similarly, take the first content on the red cell, put it here, and keep on um, sandwiching them, red followed by blue red, and so on. So every cell here has its place on this other tape. Therefore you can sort of embed this two-way infinite tape into a one-way infinite tape and continue the computation as it is.
Yes, yes.
Okay, for today's discussion we will always assume that our tape is one-way infinite because it's equivalent. Okay, so now for this language, a to the n, b to the n, c to the n, what you do is, yeah, you go ahead. So how do we design a Turing machine for this language?
So I will, when I read, like say, can you write here 2A, 2B, and 2C? 2A followed by 2, 3A followed by 3B, and then followed by 3C. So that this will help me to develop the logic.
Hmm.
Yeah, and 3Cs. So when I read an A, then I keep on replacing A by A's and then keep on moving towards right. And when I find, so I mean, corresponding to the one A, I would be replacing one B and then one C. So that is the thing. So when I keep on reading A's, I will keep on replacing A's by A's, keep on moving towards right. And when I find a B, I keep on So corresponding to first A, I replace first B by the blank or something.
You can use some other tape alphabet. Let's say you mark it like this. If you're cancelling off this A with this B, then you make it a B prime, make this a C prime. That means they have been matched against each other.
Yes, yes.
Yeah,
And in this way, yeah.
yeah. So
And yes, yes, please continue.
yeah, so in this case, you, I mean, you won't be starting with an accept state or a reject state for sure, right? So um, let's say QS is your start state. Okay, then on seeing, on reading an A, what you are going to do is you will write an A and you keep moving to the right. Or let's just remain here. Okay.
So replaces A by
A,
X
yeah,
because
A with, I'll call it A prime, maybe, so that you don't get confused. A prime and go to the right. And if there are other A's, then you are just going to skip them.
yes,
And then if you see the first B, then you're going to make it a B prime, skip over the um, yeah, then you see a C, make it C prime. Okay, at this point you really don't need to go to the right, you will go to the left and you will skip over all the okay. And now when you see an A prime, you will write an A prime and go to the right. Okay, you can sort of reuse the states here, right? So at this point you have only cancelled off this and this, and then you are going backward, all the way back. How do you know how much backward to go? The first time you see an A prime, you know that you need to go to the left now. So this is what happens here. You skipped over all the A's, you came here, and this A prime tells you that okay, this is where you need to stop, and now do the same computation again. So yeah, you could technically go back to okay. And if you, yeah, so the, yeah, the rejecting case would be that um, there are, either there are more, okay, you have exhausted A's, but there are fewer number of B's here. Okay, so maybe what you can do is simply, when you have exhausted a C, you go to Q4 and you see if there is a blank on the um, hmm, okay, let me do this again. Okay. Mm, hmm. Okay, this is where you need to check. Okay. Okay. So basically, what happened here is the next time when you go ahead, um, the next time, let's say I want to cancel off this A against this B. What will happen is I'll have to skip over all the A's. That is what we are doing here. We are skipping over all the A's ahead, but you will also have to skip over all the B primes that were before it. So this is what we will do here. Skip over all the B primes, go to the right and cancel off this B. Okay. So what could happen is there are fewer number of B's. So at this point, if you see a C or you see anything other than B, then you should go ahead and reject. Write the same thing and maybe stay, and you are going to reject. So this is not just for C, but this will happen for everything. If you see an A at this point, you write the same thing and reject. Similar, like anything could come up here. um, Similarly, if you see instead of a C, if you see anything else, then you should go and reject it. If you see an A, if you see a B, okay. And and finally, there's one more thing that you need to take care of, which is that let's say you are done crossing off all the last C as well, and you see this blank state now. So you see this blank state, you write a blank, you go to the left and go to the new state Q4, and we want to just make sure that when you go back now, there should not be any A, there should not be any B, and there should not be any C, because if they were indeed equal, then all of them would have gotten crossed off, and in the end you should get something like this. This is what you should end up getting if the number of A's, B's, and C's were indeed equal. If one of them was larger, then you would end up seeing some number of B's. So, what you do is you finally go back all the way back and see that there are no A's, there are no B's, and there are no C's. So, that is one final thing you need to do. If you see A's, just write an A, go to the left. You see B, just write a B, go to the B prime. And if you see C prime, write C prime and go to the left. But if you see any of in either A, B, or C, then you should go to reject. And yeah, otherwise, if you keep on doing this, then you should have exhausted. Okay, this is not the right thing to do. Yeah, otherwise, if you have exhausted the entire string and you never saw any of these, then you have reached the left 10 marker here, you went all the way back, and this is going to be your accept state. B. Yeah, does this make sense? I mean, it's basically the same logic that you said, but there are these corner things that we need to write for rejection.
Actually, I remember that the Turing machine for this does not used to be this much complicated. Probably.
Mm-hmm.
So, so now can I mean So, do we have a state of rejection?
Yeah, this is your single state of rejection.
Okay. Okay. So the state of the rejection is same as the trap state in the finite automata.
Hmm. Yeah.
Okay. All right. All right. Yeah. Fine. Fine. Yeah. Thanks.
Okay. Yeah. So, okay. So basically, what I'm trying to say is, yeah, this is one example where you would, and one of the classic examples where you need some state, some other state than QR and QA to begin with. Okay. Mm, yeah. Try out this question.
Show that the class of the decidable language is closed under complementation. So, since for the decidable language, I do have the answer of yes and no both. So, I just need to flip the outputs. And that would be so the complementation would also be decidable in that case. And for the second thing, show that the class of the Turing recognizable language is closed under union and intersection. So for the union thing, I mean either of them results into a true thing. So if the first returns the true, then we want I mean the second thing doesn't matter. And in the case of the intersection, I mean somehow the output of one machine will trigger the. So for the union thing, I will run both the machines in parallel. Say, so I would be having the answer of, because both the machines are Turing recognizable. So I do have the answer of yes for both the machines M1 and M2. And if I run both the machines in parallel, that will give me the union thing. And for the intersection, I mean, common thing should. So for the common thing, whenever the yes of the machine M1 comes, it will trigger the action of the second machine M2. And from the M2, if I get a yes, then fine. And for no, we are not worried. So therefore, this is also closed. And is the class of the Turing recognizable language closed under complementation? That won't happen. That won't happen because we do have the answer of yes only, and for the no, we are not sure. So how would I flip the output in the third case? Yeah, these are the answers, I guess.
Yeah. Yeah, all of these are correct. So, for the first one, let's say that L is decidable. Then there is uh, so the Turing machine which always accepts or always rejects. I mean, for every input, it will either accept or reject. Is said to be total, or decider in other words. There is a total Turing machine M such that L of M is equal to L. Then what you can do is you come up with another total Turing machine M prime, where let's say Q sigma delta QS QA QR. Then what is M prime? It just flips the QR with QA. That's all. And then what will happen is if um, if X is accepts X, then M prime would end up rejecting X, and if M rejected X, then M prime would accept X. In other words, L of M prime is nothing but the complement of the language of M. So therefore, you have a total Turing machine for the complement of L bar. Therefore, L bar is also decidable. Okay, good. For the other thing, we are asking, so let's say L1 and L2 are semi decidable languages. Um, that means if x is in L, then via M1, M2 respectively. Okay, so what that means is if x is in the language L1, then M1 will accept x, and if x is in the language L2, then M2 accepts x. Now we want a machine for the language L1 union L2. That is, if x is either in L1 or in L2, then we want to accept. Okay, so what we could do is you basically just run x on M1, run x on M2, and if M1 or M2 accepts, then we are going to accept, otherwise we reject. This is the idea, but there is one small catch with this. It is that x could be in L1. If it's not in, it is possible that x is in L2, but x is not in L1, but x should still belong to the union of the languages. Now if we run M1 first and then wait for its answer, and then run on M2 and then wait for its answer and then decide whether either of them said yes, then the issue is that if x were not in L1, then M1 is going to keep on running. It may keep on running forever. It could loop on that input, because the semi-decidable languages just say that if x is in the language, then we know that then there is a guarantee that the machine accepts. Otherwise it may reject, it may keep on looping. So if that happens, if it ends up into a loop state, then we will infinitely be waiting for that answer and we will never be able to execute this. So to avoid that, what you do is you run these machines cleverly. What you do is you run in time sharing manner on M1 and M2. That means what you do is first you execute one step on M1, then you execute one step on M2, then you execute two steps on M1 and two steps on M2, and you keep on doing this. Eventually either M1 or M2 will say yes at some point, and at that point will break and say that um, and give our answer on acceptance. Now similarly, if this were intersection, then um,
So, running X in a time sharing manner, would it be same as running both the machines parallel in parallel?
um,
You give input X to both the machines M1 and M2 simultaneously. Either of them outputs a yes, then fine.
hmm,
And as such, we are not worried for no.
yeah.
So, yeah.
Yeah, so basically, what our Turing machine model does is, by definition, it just always does one step at a time, right? It looks at the contents one at a time and then keeps on making decisions. So, parallelism would be one way of viewing it, but when it comes to simulating, the machine is sequentially doing it, right?
No, I do not think that there is any harm in giving the same input to both the machines, and both machines can be executed parallelly. So where is the
See,
issue?
M is only one machine, right? So,
So M is the one machine, but then this how do we construct this M? So like if you can draw a little diagram, like say X has been given input to both the machines M1 and M2 parallelly. Like so X, I mean X is an input, and you draw an arrow from X, yeah, not like this X and then a line. I mean, X has been fed as an input to both machines. Say there is one box for the machine M1, another
oh,
box for the machine M2. And then I give X again input to both the machines, M1 and M2.
So M1 is so um So m1 being some set of some tuple and m2 being some tuple, this is different from um, so when you say that that m simulates this, you don't it does not mean you have one tape for this and one tape for this and their respective operations. Okay, what's really happening is that there is only one tape and x is and initially on the input tape x is, I mean, you have x that's written on it. Okay, now what will happen is m is going to simulate the logic of m1 and m2 in its own tape. It doesn't have a tape for this and a tape for this. It's going to act as if, what in one step it will act like m2, in the second m1, in the second step it will act like m2.
Okay. And how to ensure that the same X has been fed to both the machines? By making some left or the right movement, because once the machine M1 has been executed, the reading writing head might have moved one step ahead, and then now this is the turn of the machine M2. So then the machine M2 must read, must read the entire string. There should not be any interleaving of the symbols
Hmm.
for M1 and M2.
Yeah, so what you can do is, you can sort of replicate, like think of this as a separator, and when you simulate the operation for m1, then you make the changes here. When you simulate for m2, then you make the changes here. Like you go here and make the changes for m1, you come back and make the changes.
Okay, but yeah, that's true. But then how will this prevent if one machine enter into the loop?
Yeah, that's what we are. So basically, you are just simulating. Think of this as, if you were at m1, then just execute one step of m1. Okay, then you go all the way here and you simulate one step of m2. Okay, then you come back and you simulate the second step of m1, and then you go back and you do the second step of m2. Okay, so if x is either in L of m1 or in L of m2, then at some kth step it will accept. Okay,
Yes, yes, yeah.
and then you will end up accepting. But yeah, if x is neither in m1 L of m1 nor in L of m2, then this machine might also end up in a loop.
Yes, yes.
Okay, yeah, and the same thing will happen if instead of union you have intersection. Then um, if x is in L1 intersection L2, then after some after some time p, both of them would have accepted by then, and therefore you will accept. If so, only difference is that or becomes and, that's all. And this was the key thing here, that we don't just simulate one after the other, but we do it in time sharing manner. Okay, and yeah, the third thing is, like you said, so um, if L is a semi-decidable language, then its complement need not be semi-decidable, because because it may end up looping in the reject case. So C is not necessarily true. Okay.
I have a question.
Hmm.
So if a language L and its complement L prime are both recursively enumerable, but then both are recursive, how can we prove?
Hmm. So I think you should, if you run the same idea, okay, so L is RE and L prime is RE, then what you do is, so let's say via M M1 via M2, then you do the same thing like you did earlier. You run M1 in time sharing manner. So if M1
Ma'am,
has,
time sharing manner means what?
yeah, so time sharing manner means you, it's not that you first run M1 on X, wait for its answer, then you run M2 on X, then wait for its answer. Rather, what you do is you only run M1 for the first step, then you run M2 for the first step, then run M1 on its second step, run M2 on its second step, and keep on doing this. So rather than running one at a time and then the other, you are stopping its computation again and again and then making progress slightly.
Okay, right.
This, yeah, I mean, why we are doing this is clear, right?
More explanation. Continue, please.
Yeah, so we're doing this so that if one of them loops and the other does not, then that will not halt our execution. So let's say if you would have run M1, waited for its answer, then run M2. What happens if M1 loops? Then you will never be able to run M2. That should not happen. Therefore, you are sort of running both of them parallel, sort of. Yeah, I mean, it gives an illusion of running it in parallel. Okay. If M1 accepts, then you are going to accept. If M2 accepts, then you are going to reject. That's it. So, why does this work? Because for all x, for all x in sigma star, either x is in L or x is in L bar, right? So if x is in L, then M1 will accept it. If x is in L bar, then M2 will accept it. So at least one of this is guaranteed to happen. I mean, exactly one of this is guaranteed to happen. Does that make sense?
So why it's guaranteed to? Why can we assure that it will guaranteed to be happen?
It will. So, why can we assume that?
Why we assure that it will guaranteed to be happen?
Yeah, because let's say this is the set of all the strings, all possible strings, okay, and let's say this is your L, and then the other part of it is L complement. So if you look at any string, either it's here or it's here, correct? So that is what this says, that either x is in L or it is in the complement of L. If x is in the L, by definition M1 will accept it, right? And if x is in L bar, then by definition M2 will accept it. So are these two things clear?
Yes, ma'am. Clear.
Okay, so therefore we are sure that either this or this will happen. If this happens, then you accept. If this happens, then you reject. That means for every string, you are either accepting or rejecting. Therefore, you are uh, therefore the language of M is recursive. So for all x in sigma star, m accepts x or rejects x. That is, it halts on all inputs. Therefore, m is a m is total, and L of m is decidable slash recursive. Okay. Okay, is this fine? Or
Yes, it's fine. But another question, I'm design a tuning machine and that convert a binary string into a equivalent unary string.
okay. Mm, um, I guess you could have probably done something like this in the class, but okay, let's do it. Convert x to, okay. Okay, so let's say that initially, mm, okay, maybe I'll take a smaller example so that if we are demonstrating, we will end sooner. Yeah, anybody wants to attempt before I solve? Yeah. Hmm. Yes.
Uh, so, like, say, let us take the string 10101, a smaller one.
Sure. Okay.
So its equivalent is 5. So
One.
it's
No, sorry. 101 is 5. Yeah.
101 is 5. So then, after when the execution of the Turing machine stops, then I should see 5 ones on the tape.
Hmm.
So if I read a one,
Hmm.
then with how many ones do I need to replace it? Because I do not know the length of the binary in advance. I
Hmm.
do not know that it is three, otherwise
Correct.
I would
Yeah.
have
Yeah.
replaced it, right? So I will replace this one by a one, and then I keep on moving towards right. Uh,
Okay. I
when I
mean,
find a G,
yeah. So this is LSB for you, right? This is LSB and this is MSB.
so I mean on the tape, will we start reading from LSB or from MSB? From MSB,
You will start from MSB. Yeah.
yes. So if MSB is one, then but when I get a zero, I need to replace it by what? I need to replace it by one, and then I need to replace it by somehow. Oh,
Yeah. Yeah. So this is the value here is basically 2 to the I times uh, j, where uh, j is the content on the tape. It could be a 1 or it could be a 0, and I is the index from LSB. So and I starts from 0. So what that means is, if you what you really want to do is somehow you get to the end. Okay, like keep going to the right until you see a blank symbol. When you see a blank symbol, you go to the left. So you are here. So what you want to do is, the value of this one at this place is 1. Okay, the value of this one at this place is 2 to the 2 times 1. The value of this 0 is 2 to the 1 times 0. That is what this means, right? So what you want to do is you read this one, and let's say I have a special symbol that tells me that the input is to the left of this dollar, and whatever I'm going to do is to the right. So when I see a 1 here, I'm going to write a 1 here. Okay, then I go to the left of this and I see a 0. If there's a 0, then you don't do anything. Then you go to the left of this, you see a 1. The value of this 1 is 4. So then what you do is you go back here and you write 4 ones.
Not 4. 2 raised to the power 0, 1, and then 2. 2 square. Yes, yes, right, right. Yeah, fine.
Okay, and then there is nothing ahead of this, so then you will stop the computation. That's the high level idea. So you will end up with 5 ones. Is that is the high level idea okay? Yeah. Okay, and then you want to, just the only thing that we did not do here is you want to maintain this current value of I. This T is something you are reading anyway, right? So whenever you are here, if you see a 0, you don't do anything. If you see a 1, then you find this value 2 to the I and you go back and write that many ones. So maintaining this counter is also easy. Let's say that whatever this computation I'm doing in this middle space. There is another separator dollar which tells me that I'm going to maintain a counter here. Okay, and how do you maintain a counter? At every step, um, yeah, you are going to double the content basically. So initially it was 1. After the first step, you are going to read this and write the same thing again. So you are going to double this. In the third step, you are going to read whatever is here and write the same thing after it. So this takes value like 1, 2, 4. Then in the fourth step, you read this, write it again. So you have 8 many ones and so on. So maintaining the counter is also very easy.
Can you analyze this first dollar symbol? After that, we can they see the all the cell fill with one. Why? But why fill with one?
You want unary, no? So you want to convert it to unary. So my unary alphabet is 1. Does that answer your question, or are you asking something
Yes,
else?
I got your answer.
Okay. Any other questions?
Ma'am, design a or construct a tuning machine to perform the binary addition.
Yeah. So maybe I'll do like a couple of questions first and then we will come back to this. So let me just write it here. If there is time, then we will do this. Um, so input to you is x1, x2 in 0, 1 star, and you want to write x1 plus x2. This is in the binary addition. Okay. So I'll come back to this after we've maybe done with um, a couple of questions at least. Okay. So yeah. So maybe try out this second question. So in the original model of Turing machine that we saw today, we had 3 choices. Either you move to the left or to the right, or you stay in the same position. Now let's say I modify this power and I only allow you to go to the left or right. Okay, this is model 1, model 2. The question is whether this is lesser powerful or more powerful, or I mean, which of these statements is more applicable?
So both would be having the same power.
Hmm.
Yeah, both would be having same power.
Hmm.
So it becomes more powerful than the standard Turing machine. No, it can only recognize regular languages. No, its power remains the same as a standard Turing machine. Yes, it can recognize all context-sensitive languages, but not all recognizable languages. No, no, no. It's will be Turing recognizable. So answer number three is correct.
Yeah.
So, but then I have a problem here at this
Hmm.
point.
Hmm.
So, like we saw in the Turing machine, only four operations are permitted. Like we are reading something, and we can replace whatever we read by something else. We can make a left move. We can make a right move. So, if I break a software, say a software which has got the front end and the back end and is doing lot many I mean modifications and the processing, and so at the finally because this everything is going to be realized by the computer, so everything eventually will get broken down into these four operations only: reading, replacing, left move, right move. Is this correct?
Hmm.
Is this correct? Like say
Yeah.
a website working, and then so if I break all the processing of the entire website handling, at the ground level, it will get broken down into these four operations only.
Hmm.
Okay. So, and if a problem is undecidable, then would it mean that that problem cannot be represented as a combination of, or as a combination of these four operations?
Yeah. So, um, the additional guarantee that we want here is that, I mean, for that language, you always want to accept or reject. Right. So if the language is not decidable, it could still be doing the same thing, right? It could just be looking at the current cell operation and then changing it and then going to the left or right. That is essentially what it is doing. But it may not end up in the accept state or the reject state.
Yes, so I mean to say that these four operations are not leading to, I mean, the combination of these four operations is not leading to the acceptance or the
Hmm,
rejection kind
hmm,
of.
hmm. Yeah. Yeah. So this is the tree that you draw, right? So you draw this current uh, your current state. This comes up, like, this is more relevant when you go to the non-deterministic um, model, right? So initially you are at the start state, then you may end up in several states because there you have choices of next operation, and then you keep on going like this. If any of them leads you to a QA, then you are going to accept. If any of this otherwise, if all of them take you to QR, then you are going to reject. Yeah, but in this case, if the language is not decidable, then it may happen that uh, you never end up, like, maybe you are just looping between two states. I mean, over and over again.
Yeah, because I'm thinking in terms of that the Turing machine is the model of the computation, and there is a correspondence in between the Turing machine and the algorithm. So
Yes.
whatever is realized by the Turing machine is an algorithm, and if some
Yes.
problem is undecidable, then yeah, so that problem cannot be represented as a combination of these four core operations, and moreover, these four core operations are going to be realized through the hardware. I mean, through the circuitry only.
Hmm.
So in that sense also.
Yeah.
So how did Turing reach to this conclusion that these are the four core operations? I mean, and using these four operations, entire gamut of the computation can be realized.
Right. So, um, I mean, so one thing is that this church Turing thesis is thesis for a reason that it's not the proof kind of, like, it's not a theorem proof. It's called a thesis rather than a theorem, um, because it's a it's more like a theoretical uh, hypothesis sort of I mean, it's not that. I mean, basically what we're saying is every computation that you can imagine can be equivalently thought of being done by a Turing machine. Okay, but there is no guarantee as of now that okay, maybe there is some other kind of computation that we don't know of, which maybe the Turing machines do not capture at the moment. The thing is, we don't know whether there is something like this. Okay, so it's not, therefore it's not called a theorem for a small gap that we don't know if there is something else. And how did Turing come up with this is so basically whenever you do a computation, what you do is you are looking at some information, you have some memory that is associated with you, you are doing some computation on it. It's like a step by step thing that it does, right? Kind of like an algorithm. You have some memory, you have some set of rules, and you are going to keep on modifying it based on the, yeah, I mean, based on what you want to achieve. So that's what this model kind of captures. The tape has is kind of like memory that you have. Okay, and these rules are telling you how are you going to change. The only thing is, um yeah, the only thing is we made it very very low level. Like we brought it all the way down to low level where um, whenever you have to do even small operations like this, like this is easy to say in English, right? You just, for every A you cancel off the next B which is uncancelled, you cancel off the next C which is uncancelled. I mean, this thing is basically doing the same thing at a very low level. So every operation that you can imagine basically does the following: you look at the current state, that like current state that you are in, and then you keep on modifying it. So there's some memory and some rules. So that is essentially what this whole model captures. Whereas yeah, maybe in one can maybe think of something that's not captured by this, but at the moment we don't know whether there is something like that.
Yes, even in the quantum computing, also people used to say that there is no violation of the Church-Turing thesis that is applicable in that area also.
Hmm.
Yes.
Yeah.
Okay, all right. Yeah, fine. Thanks. And this reading writing head of the Turing machine is analogous to the processor of the system, right?
Hmm.
Fine. So which of the following describes a tape of a standard Turing machine? Infinite in both the directions, finite but very large, infinite to the right with a fixed left hand end, and a circular buffer. A circular buffer. So, standard Turing machine, I think it is infinite in both the directions could be fine. But as you said that in this lecture, in this session, we are considering infinite towards the right and with a fixed left hand end. So either the option one and three could be
Fine.
correct. What about the circular buffer? Buffer would mean finite stuff.
Right. Yeah.
Yeah.
Yeah. So 1 and 3 are, yeah, equivalent in that sense. Hmm.
Ma'am, standard tuning machine versus normal tuning machine. What is the discriminations between the standard tuning machine and normal tuning machine?
Um, what do you mean standard Turing machine and a normal Turing machine?
Normal means not standard. What is mean by standard tuning machine? But then I will understood.
Okay, so so in the beginning of the lecture we discussed so many different variants, right? So one is what Goel had. Okay, let me just go back. Yeah, so let me just go back. So he had asked whether this can be a set of states, whether this can be a set of states, or whether we can get rid of one of the components. Other thing is, if you allow instead of one tape, can I allow like multiple tapes here? And so basically you can keep on asking questions like this, but most of those models will end up being equivalent. So whenever we say a standard Turing machine model, this is what we sorry this is what we mean, that this is the tuple you have, and this is a tape you have where the left thing is bounded and it is infinite to the right. That is that I mean, we just fix it for the sake of ease, for the sake of convenience.
Okay, fine. It's
Yeah, so basically um, whenever you see a Turing machine, you can without loss of generality assume that this is the model. Okay. Mm.
So are the following problem decidable given the description of the Turing machine, whether there exists an equivalent Turing machine with even number of the states? So given the description of the Turing machine, okay, and whether the 42nd cell of the tape is ever touched. So I think that there used to be one Rice's theorem, and that says that the non-trivial semantic properties of the verifying non-trivial semantic properties of the Turing machine is undecidable. So I mean, I don't know whether this is related to that, but whether there is an equivalent machine with the even number of the states. So I can, given the description of the Turing machine M, so I can always add few more states, dummy states into the design of the Turing machine so as to make whether there is an equivalent state and whether the 42nd cell of the tape is ever touched. So, are the following problem? Can I give the answer of yes and no both? I don't know.
So okay, to answer that, so the Rice's theorem thing is not applicable here because I mean that you'll use in questions like this, like you're given description of a machine M and you want to check whether accept if M um, I mean if L of M is finite, something like this. If you are making like if the language depends on some property of the machine, okay, then you'll be using the Rice's theorem. Whereas what we are asking here is that I have a machine M which has I mean I have a Turing machine M. Can I convert it into an equivalent machine M prime with certain properties? Like this is similar to the question that you had asked, like if I have a machine M with single finite state, is it or I mean a set of finite states, is it equivalent to a machine with a single finite state? So this is like that kind of property that we're talking about, rather
Yes,
than property of the language, or rather than the property of the language.
yes, true, true. And but since the in the question it is given the description of the Turing machine, so I guess that the encoding of the Turing machine name is given.
Mm. Yeah.
Oh, if that is the case, so whether there is an equivalent Turing machine, so I can always convert a Turing machine having the even number of the states by adding few more states. And regarding the second one, whether the 42nd cell in the tape is ever touched, so okay, so no issues. And but the tube, but since the so this second thing is not decidable because what if I keep on oscillating in between left and right thing? So I won't be able to tell you that yet. So the first one is decidable, the second one is not, I guess.
Yeah. So the answer is both of them are actually decidable. But okay, let me just write down whatever you said about A. So the answer to A is that yes, you can convert it into an equivalent. So what you do is you are given um, this description. So if size of Q is even, then M prime is nothing but same as M, and if size of Q is odd, then what you do is you introduce a dummy state Okay, so it's not reachable, there are no arrows or anything, it's just an additional state that is there, and the rest of the things remain unchanged. And now the number of states here becomes even. So this you can always do. So is A okay? Uh,
Yes, yes.
yeah, others.
Can you explain again?
Yeah, so the question is fine, no? You are given a Turing machine M, you want to convert it to an equivalent Turing machine M prime, but this M prime should have even number of states. Okay, so what you do is you are given a description of M, you go through that description and check whether the number of states in that machine is even. If the number of states in that machine is even, then M prime will be the same as M. If the number of states here is odd, then what you do is you modify M prime so that there is one dummy state here. This is a dummy state, which is, so this was your original machine and everything. What you do is you just add this new dummy state, and now this is your
What
new,
is mean by dummy state?
meaning there are no transitions to it, like there are no arrows to it coming out of it, going into it. It's just a state that is like just added into the set, but you will never reach it.
Okay, fine. It's
Right, okay. So yeah, so now you have even number of states, and yeah, the rest of the things remain the same. Okay. Okay, the second question is, you are given a Turing machine M, and you have to check if 40-second cell is ever touched. Okay, so when we say for whether 40-second cell is ever touched, we mean that let's say that these are all possible inputs. Okay, I mean 101100, you have infinitely many possible inputs. If on any of the strings, uh, if the machine touches the 40-second cell, okay, then you are, then you will say yes. If the 40-second cell is reachable for any input, it need not be for all of them, but for some input if it does, then you are expected to output yes, otherwise you should say no. Now the other thing is that, um, so I mean, you can't just, like, here is one approach which does not work. I just want you to see why it does not work. Okay, what you do is you start from your starting state QS, and you perform a reachability operation. So from here you keep on doing a BFS or something. Okay, you keep on doing going as far as possible until you repeat a state or something, and you basically are detecting whether this cell 42, yeah, it's better that I call 0 1 2 and so on, whether the cell which is labeled 42 is reachable or not. Okay, so this is something you can do because, think of this as a graph, and you are basically performing a reachability from S to T. Okay, this is something you know how to do. You do a DFS, BFS, or whatever, but this won't work. So why is that? I mean,
I could not understand. Yes, 40 second and okay. So if I look at from the reachability perspective, uh, so that is not going to work because quite possible that I keep on moving. I mean, left and the right movements, and then I never reached here. So DFS may stuck. I mean, in this kind of the configuration tree, the DFS may enter into an infinite situation that happens. BFS, since we would be conducting it level by level, so we'll ensure that yes, if we can reach to the 42nd state, this will definitely give the answer as yes. But then is this necessary that we will definitely be getting the configuration corresponding to the 42nd cell in this entire tree? That is a thing. And that cannot be ensured. But I don't know. Matlab, what is the guarantee that we will definitely be having configuration wherein the position, if I represent the configuration of the Turing machine as alpha, beta, gamma, and this beta is the state of the Turing machine, and gamma is the position of the reading writing head from where the write string starts. So then there is no guarantee here that the reading writing head of the Turing machine would definitely, in one of the configuration, the reading writing head would definitely be pointing to the 42nd cell.
Hmm.
Yeah. So maybe quite possible that we may not have this configuration corresponding to the 42nd cell here in this tree at all.
Hmm. Yeah. So yeah, but the answer, so this does not work. Maybe I'll not describe this further, but yeah, this does not work. But what will work for us is what is called configurations. So what are configurations? It's basically a snapshot of a Turing machine at a given time instance. Okay, so that means, let's say that the Turing machine is running, it's going back and forth and so on, and according to the moves that are defined by delta, and now you suddenly stop the machine at some point, and you want to, if you want to restore the computation from that point, then what all information do you need to capture that? Okay, so what do you need? You need the tape content that is there. So you want to know, when you stop the computation, what was written on that tape. So that is what sigma star captures. Other thing you need to know is which state were you in at that given point of time. And the third thing that you need to know is, where was the head pointing to? Were you here? Which cell were you at? So I'll call it I. Okay. So these three things together uh, tell you what is the configuration of a machine. Okay. So
Yeah, that's true. So this cleaning closure of sigma is the substring towards the left of the reading writing head. Is this?
towards the left of, no, this is, sorry, yeah, this is the entire content before you have all these infinite blanks.
So I mean this entire stuff, and what this Q here is the state of the Turing machine, and I is the head of this thing. So yeah, okay. In some of the books, this is written as alpha, beta, gamma, wherein this alpha is there towards the left of left string, and beta is the state, and gamma is this the remaining string, and the reading writing head is pointing to the I.
Yeah, that is also fine. So you can break this content into this as alpha and this as gamma,
Yes,
and
yes, right.
yeah, that is
But
also fine.
moreover, yeah, but then moreover, when we draw the configuration tree of the Turing machine, we do not I mean, store this entire information, alpha and gammas, and everything. Probably we just store the state of the Turing machine and whether we make a left move or the right move, that information.
No, uh, a configuration at any point of time will consist of all the the entire tape content also, even in the configuration tree. When you say, yeah, when you draw these configurations, this is what you mean, like this is the entire tape content, and this is the state, and this is I.
Okay, all right, fine.
Okay. Oh, if you're talking about, are you talking about this diagram? Sorry, somewhere I had a lot of trees or something, right?
Like say when we
If you're
draw it.
talking
Yeah.
about this, are you talking about this?
So not exactly this one,
Okay,
but
let's.
then in the general configuration tree, like say when we show that in the case of the NTM, we have a tree kind of the structure. In case of the DTM, it's a line. So there the configuration, what constitute
Yeah, I
a
think
configuration?
that is computation tree. That's not the configuration graph. So,
Okay,
yeah, the computation tree will consist of states, only the state information.
okay, okay, all right.
Yeah. Okay. Okay. So then let's look at this idea of configurations and see how that will help us. Okay. So these are the cells 1, 2, 3, 4, 5, and let's say this is the 42nd cell. And then there may be some content here. In the end, there are these blank symbols. Okay. So, um, yeah. So when will this machine ever reach 42? If um, if it kept on making a series of writes and then it eventually ended up at 42, or what could happen is it does a series of left right, and maybe eventually it reaches to 42. But one issue with keeping track of just the number of lefts and the number of rights is that it could get stuck. It could get stuck in a loop, right? In one step it will say go to the right, in the other step it will say go to the left. So in that case we are going to get stuck and will not be able to check if it ever reaches 42. So what you do is you find out, the question is what is the total number of configuration and let's not look at what is here, let's just look at this set of 42 cells and ask what are all possible configurations that we can have on 42 cells. Okay, so what all possible configurations are there? So when you say a configuration, what is the content, what is the state, and what is the index position? So where all could it point? There are 42 possible choices for the um, for the head. So these are 42 possibilities. The number of states is size of q, and what all contents can we have on this? How many possible contents can there be on this tape of 42 length?
So I mean, what all content? So for every cell, we have tau many number of the possibilities.
Yeah, you have.
For 42, I would be having tau raised to the power 42 number of the
Yeah, for
possibility.
every cell there are size of gamma many possibilities, so independently you multiply for all the possibilities, so you have these many uh, size of gamma to the 42 many possibilities. So what is the number of configurations? Number of configurations is at most gamma to the 42 times size of q times 42. Okay, now the claim is that if the cell ever reaches 42, okay, then it will have to um, it will have to cross one of these configurations. If it never touches 42, then it will repeat one of the configurations. Okay, so is it clear that if machine M reaches a configuration C1, then it reaches a configuration C2, and it reaches a configuration C1 again? Okay, then is it clear that what can you say about this machine?
So, since the number of configurations are two, so two different configurations are possible. So, since there are only two configurations possible,
No, what I
so the
mean,
answer is no. Answer is no in this case.
no, what I mean is there is a series of configurations that will take from C1 to C2. There are some things in the intermediate, but it is possible to reach from C1 to C2, and then from C2 there is a series of configurations that will take you back to C1.
Yes,
Yeah, then M loops, right?
yes, yes,
Right. So, so if you can detect a loop within these many configurations, okay, then that means that the machine never touches the 42nd cell. Or actually, I should be doing 41 here. So, yeah, is that clear? So, if there is a loop in this set of configurations, then M loops without,
yes.
yeah, without reaching 42nd cell.
So,
Otherwise,
yeah,
yeah.
41 is the key here. 41 is the key here.
What is the, sorry, what?
41 is important here.
Yeah,
If
41 is important. Yeah, yeah. So, let me, yeah. Hmm. Yeah. Even here. Yeah. Otherwise, if there is no loop, that means from it will follow a path. From C1, it will go to C2 and so on out to C whatever this number is, CK. From here, it will have to go to a new configuration because there is no loop. So it will have to go to CK plus 1. That means it will have to touch the 42nd cell. And the reason we only care about this part um, of the tape is that in order to modify anything here, you will have to reach 42 first. Without touching 42, you can't go ahead and modify any of this. So therefore, you can safely discard this part and just focus on the first 42 cells or 41 cells.
yes, yes, right, right. But the number of the possibilities would be huge, isn't it? To be
Yeah,
explored.
huge, but yeah, finite is enough for us. Like we
Yes,
don't, yeah.
right.
So, others, are there any questions or any part of this that you would want me to repeat? Is this clear, Saurav, Vasanti?
Yes, ma'am, it's clear, but you were asking that others arise a question from others schedule module. So I have a question. So construct a tuning machine to perform the binary addition.
Yeah, so Okay, these are not the questions from the assignment, right? I haven't checked the assignment.
No, this I collect from another person.
Okay, okay, sure. So, huh. Okay. So, so there's some part of the tape that is occupied by x1. Then there should be some separator that tells you that x2 starts here, and then you have blanks. Okay. So, how do you perform your um, let's say this is x1 and this is x2, then how do you perform your binary operation? You first look at the lsps of both the inputs. Okay, if both of them are 1, then your lsp is going to be 0, and then you carry over a 1. Okay, and then you're going to look at this bit of x1, the uh, second least significant bit of x2. Look at these two values, sum them together. The bitwise sum is something that you know how to do. And then look at the carry bit. At every point there are three things that you are looking at: uh, a particular bit of x1, a particular bit of x2, and this carryover bit. And then you do a sum of all the three. Okay, and you write it here. So when I say write it here, this is your x1, this was the dollar separator, this was x2, this is the dollar separator, and here you are going to write your sum. Okay, so it's okay if you write it in the reverse order first. So first, 1 plus 1 is 0, so you are going to write a 0 here. 1 0 1 0 1 and 1 1 1 1. So you looked at this bit, and you wrote a 0 here, and you are also carrying this is your carry bit. Okay, so at this point the carry bit is 1. Okay, then you think of it this way, as you did earlier, like replace these with new alphabet so that you know that they have been crossed off. You look at this second least significant bit, that is 0, second least significant bit, that is 1. So the sum so far is 1, but the carry bit tells you that you should be um, yeah, you should be adding this 1 to it. So the second bit becomes, sorry, the second bit becomes 0, and you are still carrying a 1. Then you look at the third bit here, add them together. So 1 and 1 is 0, and then you are again adding this 1 carry bit, so this becomes 1, and you are still carrying a carryover. Then you look at this bit here, this is 0 plus 1, which is 1, and you add a carry to it, that is again 1, and you are still carrying over. Then you look at the MSB here, there is nothing here, so you are just going to add this bit and the carry bit, so that gives you 1 0. And notice that, sorry, 0 1, yeah, notice that this is your MSB and this is your LSB. So if you want to output MSB to LSB, what you can always do is read the input from left to right and reverse it. That is something you know how to do. So yeah.
Why to go for this one? I mean, we have already seen converting binary into unary. I would have converted the first binary into the unary, second binary into the unary, and put both the unaries side by side, and that would be the total sum of the two binary sequences.
Yeah, but then he wants the output in binary. So then you would again have to convert the unary to binary.
Well, the question was just to add two binary numbers and nothing else, I guess.
Uh, yeah, but I mean, when nothing is mentioned, you generally always uh, work with the binary alphabet. So, I mean, these questions will actually become relevant. Like, yeah, you have seen circuit complexity, right? So, these questions become relevant in that context where you had these NC1, TC0, all these circuits, and you wanted to check whether addition of two inputs can be performed in NC1 and so on. So,
Yes.
yeah. Hmm. Okay, but yeah, does that answer your? But yeah, if we don't care about the answer being binary, then yes, you can use the same logic. Just convert both of them to unary and append them together.
How can we draw a trace transition diagram?
Mm, yeah, you yeah, you try it out. I'll draw. If something is wrong, then yeah, I mean, yeah, we can discuss on the fly. So let's say QS is the start state. Then what do you do? What is the first step? Like, let's I mean, yeah, if the set of steps is clear, then you can convert it into the diagram easily. So tell me what is the first step. That will tell you the arrows to make.
Then second state,
Okay.
we move second state. But here, what is the intermediate state input? What input will be required? So that is the question.
The input that's given to you is in this form. You have binary string x1. Then there is a dollar separator that tells you that after the dollar there is x2.
You go ahead, then I will think first.
Okay. So first thing that you want to do is okay. So the first thing that you want to do is um, go all the way to the right, and you're going to mark a dollar symbol that tells you that from that point on you're going to store um, the sum that you want at the end. So what you will do is if you see a 1, you write a 1, you go to the right. If you see a 0, you write a 0, go to the right. If you see a dollar, you write a dollar and go to the right. Then if you see a blank, you write a blank and go, you write a dollar and go to the left. And
Ma'am, how can we guess self loop transition for a dollar such that the dollar are one such that one are and zero such that zero are? How can we guess?
you are not guessing, you are saying if it's a 0, you go ahead. If the symbol that's written is a 1, then you write a 1 and go to the right. If the symbol that's written is a 0, then you write a 0 and go to the right. And so on. We are not guessing, no matter what it is, this is what, for every possibility, we are saying this is what we will do.
We can go left also.
Yeah, but right now, what is it that we want to do? We want to go all the way to the right and put a. So initially, you only had x1 followed by dollar followed by x2, and then there were blanks. What I want to first do is I want to put this separator out there so that from that point, whenever I go ahead, I will see the final answer that you want, the summation.
Okay.
So this is like a sanitary check that you need to first do so that later on we don't get confused. Okay, so then whatever you see from that point, you are just going to keep moving to the left. um, dollar left. So now you are back here, back at the first starting position of x1. And okay, so okay, I can actually skip over that, so let me do that. So what you'll do is you only cross off all the x2s. Okay, so you cross off all the x2s, that means you see a 0, keep going to the write the same thing, go to the left. Now if you see a dollar, okay, that means where are you now? You have skipped all of x2s, you have seen this dollar, you move to the left, that means you are now reading an LSB of x1. So you are reading an LSB of x1, and you want to read the LSB of x2. So what should you do? You should go back, yeah, you should go back all the way here and find out what is the LSB of x2.
Okay, ma'am. Second transition for self loop. So 0 0 0 0 L 1 1 L, but not given uh, dollar R L. Why?
Yeah, that is
It's
here
possible.
because yeah, so because I want to now distinguish. So if you do dollar L, what will happen is it will uh, it will keep on going backward, right? So you are at q1, you do dollar L, you will move here. After that point, if you see a 0 or 1, it will keep on moving to the left or right because of this transition. But I don't want that. I want that the moment I see a dollar, let me just look at the LSB of x1, and then I want to do some operations, right? I want to add this LSB with LSB of x2 and then write the summation here. So you want to distinguish between these two states, right?
Yes, ma'am.
Okay, so at q2, okay, so at q2 you have read, um, let's say you have read a 0, and you write a 0, you're going to replace it with 0 prime, and you go to the right, and let's say this is my q0. If you see a 1, you are going to write a 1 prime, and you are going to, let me call this p0 and p1. Okay, so why did I do this? You it doesn't matter whether you make two separate moves or not. You'll just have to do a little more work if you don't make two different states. The reason I did made p0 is that p0 is the state that remembers that this bit of x1 was a 0, and p1 is the bit that remembers that this bit of x1 that I'm currently looking at was 1. So now if you are at p0, what you do is you go to the right. So skip over the dollar, go to the right, and q3 you skip all the zeros and ones. Skip the zeros, skip the ones, and then eventually you'll see another dollar. Like if you have skipped all of them, you will see another dollar here. So you skip over that dollar, and now you are looking at the LSB of x2. Okay, now you do the same thing. If the LSB was a 0, then yeah, P3, P4. So if the LSB was a 0, what that means is the LSB of x1 was a 0 and the LSB of x2 is a 0. So the summation should be 0. Okay, the new bit in the summation should be 0. Similarly, if the LSB of x1 was 0 and the LSB of x1 was 1, then the summation should be 1. Okay, similarly you will have this kind of splits based on what is the LSB of x2. Okay, and in that state you are going to remember whether there is a carryover of 1 or whether there is not a carryover of 1. So once you have done this, what you do is you are already here, you skip all the way to the dollar and you write whatever the sum is. So initially there are all the blank symbols.
What is mean by zero prime? Why zero prime is
Yeah,
appeared in this form?
yeah. So why are we doing this? Because let's say you did this sum and you did this sum, you went ahead and you wrote it here. Now while coming back, you need to remember which sum you did, right? So you somehow are sort of crossing off that okay, this is something I did and this is what I want to look at. Otherwise, if you don't do this, the tape cannot distinguish between the one that you had read earlier and the one that you now want to read. Similar to that A to the N, B to the N, C to the N. While coming back, you want to make sure that you are not reading that same A's, same B's again. Uh, does that make sense?
Yes, ma'am, it's clear.
Okay, so I'll not write the rest of the thing, but yeah, you can finish off this diagram.
Okay, thank you.
Okay, good. Um, okay, so yeah, I think it's 9, so maybe I'll let me stop the recording. I hope the session was useful.